Okay, so guys, we'll have today's talk by Usha. Usha Lokala. She has been a PhD student, but she's defending next week. I mean, in a week or two.
Yeah, in 2 weeks.
In 2 weeks, and so now you'll be able to see, an example of what comes towards the end of a whole bunch of research of several years. She's going to talk about the topic of understanding natural language more than just NLP, natural language processing. A lot of things like when you summarize a text, that's the natural language processing. When you're doing typically question answering, as currently using LLM, that is generally natural language processing. But actually understanding the natural language has is more challenging, and using knowledge in being able to understand natural language is the topic of her work. Her work is done and demonstrated in the context of social media and healthcare. So here you are, Usha.
Um, Good afternoon, everyone. My name is Usha Lokala, and it's glad to be here and present my dissertation defense well before the actual date to you all. So your feedback is much appreciated on this. So the topic of my dissertation is knowledge and ontology enhanced approach to natural language understanding. I know it's too wordy, but that is what I came up with. And so the area of application is computational social media and healthcare. So you're going to see a lot of social media data discussing pipelines on how to analyze the desired output from social media data and clinical data and stuff. So with that, let me. Okay. Okay. So these are the building blocks. So we're going to discuss some motivation behind our KOE-NLU and some tasks and challenges and pipelines and then applications. So you'll also see my research contribution and technical contributions and novelty and the future research directions. And that ends the presentation today. So I would like to talk a little bit about my PhD journey here. So I completed my bachelor's in computer science at JNTU Hyderabad, and then I completed. So I got to work with some technical giants, corporate giants like SAP Labs, Infosys, and ITC. So there I worked in the area of supply chain management, both functional and technical modules. And then I came to United States to pursue my master's in computer science at Northwest Missouri State University, where I did my first paper. So those days are of machine learning, and it was just budding in 2015, and I did my first paper on support vector machine. So later, I got an opportunity to join my PhD at Wright State University, where I met Dr. Amit Sheth. But there I have also done a graduate study in big and smart data sciences. And later when we moved to a institute, I'm here, and it's been a long journey. And it's a great honor to do my PhD with Dr. Amit Sheth to be my advisor all along since 2017 fall, I guess. Okay. So yeah, I'm going to talk about this more at the end of the presentation, but let's move on to the. Okay. So what is knowledge ontology enhanced NLU? So here, so I'll talk a little bit about how NLP versus NLU in here and the applications of it and the advantages of using NLU. So we get enhanced context awareness, unlike in natural language processing, and improved reasoning and better alignment with domain-specific knowledge. And the applications include summarization, question answering, conversational dialogue, and better entity recognition and intent understanding. So to explain further on this slide, I highlight here applications of NLP limitations here, like presence of long tail, which I'll be giving example for each of these, contextualization, abstraction, personalization, and reasoning. So this is where KOE-NLU comes into picture, and the real impact will be in the area of real world health applications with trend detection or decision making using social media or clinical data. So what do I mean by presence of long tail here? So suppose if you consider this statement, it's quite complicated, like opioids, it talks about opioids and recreational and medical purposes and pain relievers, and talks about opioid overdoses and stuff. So if I have to answer a question like this, like does fentanyl cause opioid overdose? The system needs to understand this long tail, right? So process of learning with the long tail would be difficult with just natural language processing alone. So because this is too domain specific and maybe low resource data, and also there are many entities of interest to understand to come to a conclusion if fentanyl causes opioid overdose or not. So understanding this will not be possible without a domain specific knowledge graph or ontology, right? Okay, coming to contextualization. So what do I mean? What do I mean by contextualization here is it refers to incorporate both linguistic context and also situational context, like it can be cultural or maybe related to speaker identity. If it is a dialogue system, it may be related to speaker culture or something like that. And so we need to leverage a context-aware language model here, and I try to understand. For example, here we are talking about effects of depression. So we can easily understand that suicide and leading a person to attempt a suicide. So depression is capable of such things. So here we took an example of concept net to understand the entities of depression here. That is like a single knowledge graph here to contextualize things. So that in a chatbot situation, it responds to a user appropriately in case if they are depressed. So it needs to understand all the surrounding sentences and concepts related to depression in this case, which we call contextualization. Again, limitation of NLP. So other limitation is abstraction. So this is a task of mapping low-level features to higher-level human understandable abstract concepts, because humans often communicate in higher abstract concepts instead of lower things. So to better explain decisions or ideas to other, it's often we often try to extract the abstract concepts of low-level concepts, which is again not possible without concept net or without such knowledge graphs here. Okay, so coming to personalization. So here there is just a dialogue going on between depression and gender related cardiovascular symptoms and stuff. So here identifying data point, specific information and integrating with knowledge graph, integrating with with external knowledge to construct a personalized knowledge source, which is what we call personalization here. For example, a person's depressive disorder can be due to family issues or relationship issues or clinical factors like this. Here, the context is CVD, cardiovascular disease. All of these affect the context specific to an individual, and there is a need to study a gender-specific symptoms here. Like woman can describe the symptoms differently compared to a man, right? So, which is again NLP limitation. And next we have reasoning. So this text here is more of substance use disorder than mental health related. But when we ask the model on why is this mental health related, on why or why model or why the model predicted depression, so the model is not able to interpret it and it says unknown. So there is no explanation why it is not, as it is not inferring any domain knowledge here. So these are the limitations that we are trying to address in this study. So this summarizes all what we have discussed. So language models can better understand the context of user queries, and to provide more accurate and relevant responses, we need KOE-NLU approach for improved context accuracy, and we are going to discuss more on process knowledge in the next slides. Okay, these are the problems we solved in the KOE-NLU scenario, and I'm going to discuss the ones highlighted in bold today. So starting with process knowledge guided language prompting to automate main concept analysis. Let's discuss what is process knowledge first. So it's a step-by-step procedural understanding of task, as we already know. And I'm going to give a good example of how to understand this process knowledge better. But it requires domain expertise, and it all obviously requires workflow details. And the best example is manufacturing step. And the next good example is a clinical guideline on, for example, to detect depression as per DSM-5, or to detect the anxiety as per some clinical guideline. So such things require an event flow for the model to understand an event flow. And when the process knowledge is integrated into the learning model, it ensures uh, accuracy and context awareness here. And it also minimizes hallucination and confusion in our language model responses. So that is in short, but let's discuss that in detail. Okay, so this is how I define process knowledge in healthcare. So it's a learning paradigm that layers clinical process knowledge structures on language model outputs, enabling clinician guided model of the underlying language model predictions. So here, if you observe, we have a human loop feedback in here to analyze the output and again reflect back. And also we include the workflow or the event flow or the process order of how we achieve to a decision. For example, if the person is suffering from depression or not, something like that. Okay, so this ensures the language model outputs are aligned with the clinical process guidelines, making explanations more relevant and applicable to medical scenarios. So which then moves us to understand why process knowledge matters in prompting. Okay, so this example is taken from a pet data set. So so this motivates us to understand why process knowledge matters in prompting language models, why to integrate process knowledge in the learning process. So this is, as you can see, this is a multi-turn dialogue system. And we have an artificial agent here, which is a domain expert that is guiding the construction of process knowledge graph by answering the user. So here, the user poses specific questions to extract these conceptual elements and guide this. So we plan to use this information to construct KG and to construct the workflow here. So in the first task, if you see, the user asks for the list of activities of a process document to add activity notes, which are green squares over there. And in the second step, the user asked a domain expert for the list of actors who are responsible or who can perform this action, right, which are yellow squares. And there is actor performer relation with yellow dashes to the KG. And in the last step, user asked for the set of temporal relations. So when can the claim happen, or what is the timeline of it? So there is some temporal aspect to this too. So this is how it typically works when you want to file a claim, or what happens when you send back the claim, who is going to act on it, and what is user expecting. So something like that. So this is a very good example of a process knowledge, knowing who, what, when, and how of a workflow. So this who, when, what, and how of a workflow, without understanding this, the LLM predictions won't make any sense if you are trying to automate this process, right? Okay, so these are some existing approaches to integrate process knowledge, like neurosymbolic integration, where we combine symbolic, rule-based, and data-driven AI techniques. And we have domain-specific LLM fine-tuning, which is a good old technique to do this. And we have a human-in-the-loop feedback with reinforcement learning, correction errors, and guide the learning system. And we have knowledge fusion across sources, like maybe our cross-attention mechanism across domains, or knowledge infusion based techniques from various domains of knowledge. So yeah, these are good old approaches to integrate process knowledge. So that is the background of this process knowledge integration and why we need it. So that with that, I would like to introduce on what we have worked on in this research. And I would like to introduce to something called main concept analysis and why to automate it, and what is the process knowledge in MCA, and the novelty and technical contributions of our work. Okay. So this is a discourse data where we see cat rescue picture and cookie theft picture. So it is so basically it's a black and white drawing. If you see the first picture of a girl trying to save a cat from a tree. So these tasks are used in aphasia therapy. Basically, in the subjects who are suffering from cognitive impairment, to assess their language skills. Okay, so in this task, a patient is shown a picture, either of these pictures or both the pictures, and we ask them to tell a story about what's happening in the picture. And the patient is asked to include beginning, middle, and the conclusion of the story, and the patient can look at this picture while he or she is describing this. So that is a discourse task. So this is time intensive, and when we analyze like more than like 1,000 patients or so, it becomes really difficult to scale the process up, and there is a need to automate this, which we call like a main concept analysis. But before we go to that, let's try to understand what is MoCA. So MoCA is nothing but the rightmost picture that you see. It's a popular test again to detect cognitive impairment, and it is attached along with these results to analyze cognitive impairment. So we did work both on detecting cognitive impairment and also to automate main concept analysis. So that's the reason I'm trying to build a background here. So this MoCA will test memory, executive functioning, attention, language, visuospatial, and orientation with all the questions that you see on the rightmost thing. And it is scored on 30 points, and that data is also used along with the discourse analysis, which is a language-based analysis on the left side, to predict cognitive impairment. Okay. Okay, that takes us on what is main concept analysis. So MCA is a discourse assessment that measures the informativeness of a discourse sample related to picture description task. So what do I mean by that? So we want to test how accurately and completely a person discourse text is able to summarize that picture that you have seen in the previous slide. Basically focusing on key elements like main verbs, like critical details, nouns, and stuff like that. So I'll show you an example on how the main concepts look like. Okay. So for an example, in a cat rescue description picture, so the cat is trying to save, the girl is trying to save the cat, and the cat is sitting on the tree. If discourse analysis looks like this, so we always look for extraction of main concept from the transcript, I mean from the discourse text, And if the main concept is not produced, then we code it as absent. If all essential elements in MC are present, then we code it as AC or IC, which is accurate and complete, or inaccurate and complete. So we have 5 codes at the end. So this is a process knowledge for us to automate the main concept analysis, to come to the conclusion. And there are different conditions to prove if it is accurate or complete. Okay, so these are the examples for the cat rescue picture. This is how a main concept looks like. The little girl was riding her bicycle, and we look for she, if even if a person uses she or the girl or the child or any girl's name, we consider that. And this road rides is playing on, for example, these are all considered alternatives for this riding. And then instead of bicycle, the patient can use bike, tricycle, or trike. So similarly for all the main concepts in here. So these are the 5 main concepts in the cat rescue picture. And this is the real patient discourse text coding that they're manually doing currently. And they arrive at a score, how many ACs. So we discussed those labels, right? How many ACs, IC, AI, II, and AV are found. So as I said, these are different conditions for coding it to be accurate and to be complete. And these are the coding guidelines. So if you see this, this becomes process knowledge for our study here. Okay. So we tested this on several knowledge guided prompting approaches. So one is graph based prompting, where we capture and organize domain specific process knowledge such as concepts, reference sets, and scoring rules into graph. And the other method is we have process templates as few short examples. So we explicitly give some examples, but instead of giving some arbitrary few short examples, we build the template-based examples that reflect the actual main concept analysis. And we have constraint-aware decoding, where we work with schema definition. So this enforces domain-specific or logical constraint at the inference time, and it helps control the freedom of these language models by pruning the hallucinated content. And we also worked with ontology driven prompting. Okay, so these are the existing knowledge guided prompting approaches that we worked with. So the contribution for this work is our proposed approach, adaptive graph guided process knowledge language prompting, process knowledge guided language prompting. So what do I mean by that? So these are several components of this adaptive approach, where we have graph construction, multi-stage prompting, and adaptive self-correction paths. So here, unlike conventional PKG-LP approaches that we have seen in here, which rely on some kind of chain of thought pipeline, this explicitly encodes domain knowledge as a weighted graph, right? So our domain knowledge is our nodes as the nouns defined in the MCA, and the actions and verbs that we expect, and the accuracy, completeness, and the when we consider it accurate and when we consider it as complete, we have a weights for each of those features. And that's how we construct this domain knowledge graph, which helps us to constrain our LLM answers. So once we get the answer from LLM model, we embed a short violation report, like to reprompt the LLM in case if it is breaking any domain constraints. So we look for an output and we look for synonyms of it, and we are okay. We are trying to mimic a human, how would a human code in here. So this step of generating a violation report and reprompting the LLM to do better. So this is fully integrated into our pipeline. So, and it boosts reliability in main concept analysis. So in terms of presence, I mean presence of a main concept in the text, and then accuracy and completeness, which is crucial, which is a deciding factor in MCA. Okay. So as I said, our nodes here for domain knowledge graph are main concepts that we identify in the discourse analysis, and the synonyms of it that user may use, the patient may use, and potential common confusions like walked versus ran or something like that. And then edges would be for the knowledge graph, validity or dependency constraints like presence, accuracy, and completeness rules. And then we have weights on how much importance that we give to the concept or a domain priority in this case. So we don't want to miss that girl, right? And the user is allowed to use any girl name or the cat name. So he or she can use a cat name as Sally or something like that and still get it to be accurate. So we're trying to build a domain specific KG in here. And we have multi-stage prompting. What do I mean by that? We have extraction prompt that focuses on capturing concepts with minimal domain constraints. And we have validation prompts where we check if each concept aligns with the known synonyms that are defined in the knowledge graph. And we have scoring prompt. That is just a numerical domain scales for, as I said, for completeness and accuracy and the presence of the main concept. Okay, then we have adaptive self-correction, which is a novelty in here, where we have violation detector. If algorithm is comparing, comparing LLM's output to the DKG constraints. So if you get a completeness score above 5 or something, it needs to recorrect, and then we generate a short correction prompt at that level to basically compact actual input, explaining each violation, how it violated, and requesting a fix from LLM. So that is one adaptive self-correction we have made in this AGG PKG And then we have human loop in this as feedback and reinforcement. So we ask clinicians or domain expert to see the final annotated examples, annotated transcripts, and to accept whether it is correct or not. So this will flag the corrections made, and it will adjust the graph weights in the domain knowledge graph. So and it will help us to uh, make better prompt instructions. So that is the technical contribution over here. These are the results we got. And for different approaches, and this is the ablation study we have done. So this is our full model approach, and here we have no weighted graph where we don't have a DKG, and here we only have a single stage prompt instead of multi-stage prompting, and there is no self-correction and no human feedback. So, and these are the observations that we have made in the ablation study. Okay, so that is that. With that, I conclude the process knowledge guided language prompting method to automate my main concept analysis. So next step we have taken is to analyze cognitive impairment using process knowledge, which falls into the same theme. So I discussed already what is discourse analysis. So MCI here is mild cognitive impairment, and so it affects many aging adults. 1 in 9 adults have MCI, and we have scalability issues as of now, and it had become expensive in clinic procedures to do all these kinds of discourse analysis text. Basically, they record the discourse analysis and convert into text, and then do the analysis on that text. So they only have audio descriptions of those pictures at first, and then they have to do all the work, and they have to make them take the MOCA test. And here basically we are trying In this study, we are basically trying to eliminate the MOCA test itself and only see if we can depend only on the discourse analysis to predict MCI or not. So that is the motive behind this work. So we worked with aging brain cohort on both of these works, and we have taken input from them on what they are looking for in here. Okay. So there is a research gap. So the research gap we found is lack of automation and non-invasive diagnostic tools. And there is a limited use of discourse data in, say, cognitive impairment detection. And there is no comprehensive feature analysis. And as I said, as I mentioned, scalability and accessibility issues are there in the MCI study. So from the audio description, we convert it into text, and then we have all this semantic, lexical, fluency, and sentiment data that we get from the text, which we use as features to predict MCI. As we have audio description itself, we have acoustic analysis data like this, like pitch, harmony, shimmer, total duration on how much time the patient took to describe the picture and stuff. And we also have demographic features. And we came up, so this the summary looks like this. So we have a picture description task here, picture description here, and then we have all these language measures and audio and language measures, and we have semantic, syntactic, and lexical features. And then we also worked with demographic and demographic audio and language features. So this pipeline okay, this pipeline here summarizes on what we talked. So these are the picture description tasks that goes into discourse data. Here we have MoCA features where I mentioned this visual spatial attention and the other 6 features that are coming from MoCA as assessment factors. Now we used all these features and we build, this is our model, which is cross cognitive domain attention model that also uses ConceptNet to predict cognitive impairment, MCI or not. I think some slide is missing. I have a slide missing here to explain the CCDA mechanism. I apologize for that. Not able to see it in here as well. Okay, so these are the results of the study. So we have a discourse text and we have a MoCA score attached to it, and we have a label. So we are able to predict both MoCA and the mild cognitive impairment or not, and it falls across 3 labels: MCI, possible MCI, and healthy. And this is how the picture description task looks like. Okay. So when we consider that ends up a study on process knowledge guided analysis, and this I would like to talk about diverse sources of knowledge towards natural language understanding. As you know, here semantic knowledge includes keywords, topics, emotions, and all, while structured knowledge has comprises knowledge graphs, knowledge bases, and data tables. And we used and created as part of this work a drug abuse ontology in our study. And I would like to give some motivation on why knowledge ontology can be used as knowledge source. So ontology differs from a knowledge graph, and it can be tailored to specific domains. For example, if you would like to work on drug use, or if you would like to work on something like main concept analysis, it is always beneficial to build domain specific ontologies, because that specifies relationships between entities, properties, and concepts to that particular domain. Okay, so let me talk about how we constructed drug abuse ontology in here. So this provides an overview of DAO. So we used Prodigy, a popular ontology editor, to construct this ontology, and it has concepts related to substance use. And we have classes of substances like opioids and cannabinoids, and this was created and populated with all the concepts, subtypes of substances, for example, morphine, fentanyl, and each substance is defined by its name. And wherever it is applicable, we also added information like pharmaceutical name and brand name and slang or street name and chemical formula of it. So this, okay, I have highlighted here an entity of cannabis and its related terms that is derived from the ontology. Okay, this is the structure of drug abuse ontology, and here we see instances in purple. So these are the instances. So this is like creating instance of a class in a hierarchy. So the instance of a class here, it has its own class and it fills a value. So instance has its own properties again. And for example, fentanyl belongs to a class opioid, and it has its own properties such as brand name, synonym, slang term, etc. And this ontology reuses instance from DBpedia dataset. For example, buprenorphine, that is extracted, all that information is extracted from that DBpedia. Okay. So this describes how the texts are automatically annotated using the DAO, and we identify drug entities, dosage, time interval, and route of administration. So without DAO, identifying such a level of deep information is not possible. So this becomes really useful in tasks like lexical, semantic, or syntactic analysis of textual data, which makes ontology an external source of knowledge. And also we are able to identify triples and entities in the data. And this is a very good example of contextualization, and ontology here acts as a prior requirement for processing any further information. Okay, so this is how we evaluated ontology using tools like OWL, Community Ontology Repository, COR. So we looked for criteria like impact, reusability of ontology, design and technical quality, and availability. And these are the standard tools to evaluate ontology. And we call it, they call it a perfect O ontology improvement on checkup levels on how they evaluate the ontology. And DAO passed all the levels, starting from syntactic validation to ontology consistency. And those are the tools that DAO is already available on and loaded. So these are the descriptions of tools used to evaluate DAO. And these are the results. So these metrics list the numbers for structures and representation of ontology in Prodigy. And this is how we evaluated the ontology, and these are the counts of how many axioms and uh, data properties and annotation assertion are there. Okay, so Dr. Shah, we still have time, right?
10 minutes.
Okay. So let's move on to another work, how to understanding mental health symptoms using knowledge infused multitask learning framework. So this talks about personalization, or this is the framework of social media posts that we have used. So the problem we are trying to solve in here is we have a lot of social media data from Reddit and posts related to depression, all the mental health symptoms related to cardiovascular diseases among men and women. those posts that we derived from subreddit, that this is how the framework is designed to do this analysis specific to a gender. So this is a research gap we found. So existing research often neglects the gender-based differences in the expression of mental health symptoms, and there is lack of study that simultaneously consider mental health symptom, particularly in the context of gender-related differences. So these challenges remain, and that makes us to detect or distinguish between multiple or coexisting mental health symptoms in the same social media post on in that scenarios like that, and there is a gap in developing computational frameworks too that can inform gender sensitive healthcare intervention based on social media data. Okay. So we develop a computational approach here to understand the gender-based mental health symptom on social media. So our approach here is a knowledge-aware, task-adaptive based bioencoder model, which simultaneously identifies these mental health symptoms and the underlying gender information. And we call it as a GEM, gender-enabled model. So the performance of GEM here is improved for the task of symptom identification along with the task of gender identification in a multitask learning paradigm here. And we compute attention over these two encodings for generating a mental health context aware representation of a gender text. So we have a gender text and several mental health symptoms are mentioned in that post, and we try to compute attention over both the two encodings in order to achieve a context-aware representation of both gender and mental health symptom. So these are the results of the model. We have a post and comment here, and the case we're trying to identify here is a symptom. So actual symptom is anxiety, and these are the predictions that model made, and GEM is the proposed model, and yeah, the next is the gender prediction, and those are the predictions that other models made. So the technical contribution of this work is our GEM framework, where we propose a bioencoder model that separately encodes symptom and gender text, and we have attention mechanism to create mental health context aware. Mental health symptom aware representation of gender language, and by integrating gender embeddings and with word embeddings and applying a multi-head attention mechanism, this model is capable of focusing on gender-specific language along with along with the mental health symptom associated with the gender, which enhances its performance in tasks like differentiating symptoms for each gender. So the key steps here involve concatenating embeddings, performing linear transformations, and applying dot product attention across multiple heads, and then combine the results of those attention heads for the final representation. So that is the technical contribution of that work. So we again go back to the drug abuse ontology to understand cannabis and synthetic cannabinoid use. And this is the motivation on why we would like to study cannabis on social media. So to analyze characteristics of marijuana users and describe patterns and do some trend detection in knowledge and attitudes and behavior related to cannabis on social media. So doing this kind of study is not possible without external knowledge source like drug abuse ontology, because we build a domain specific ontology to study this kind of to do this kind of research on social media data where generalized models cannot do without external knowledge source. Okay, here we have entity locator module, and there is this input post going on. So entity locator module here is using our drug abuse ontology to map input words in that tweet to their corresponding entities, high-level concepts in the ontology. So the process involves computing the edit distance between the entity names on how far they are located in DAO, and the identified entities are then masked to provide the model with explicit entity information. Okay, so for example, the terms related to all cannabis terms are normalized to cannabis, and all the terms related to depression are masked as depression in that post. And you see the right hand side post. And we classified each post into reason, either reason, effect, addiction, and ambiguous. Those are our categorical labels in our data, and we are trying to predict or we are trying to classify each post in any of those 4 categories. For that, we have built a pipeline which we call a gated knowledge BERT framework. And this consists of 3 main modules. We have entity locator module, which we discussed in detail, and we have position aware module and encoding module. And in position aware module, we have position embedding layer, where it is inspired position encoding vectors. So this layer will compute the relative distance of words in the tweet to the identified entities in the ontology. And we have convolution layer and entity position aware attention layer. That means how far it is located from that entity. So for the depression terms, how far it is located from the depression entity, and for cannabis related terms, how far it is located from the cannabis entity. And it computes attention weights based on the hidden states and aggregate them. And then we have encoding module, and we have BERT representation. And we have a new thing here, which is we call as a gated feature fusion, where we combine the features from BERT and the position aware module effectively to achieve the result. And then we have a feed forward network with a softmax layer to classify each tweet into those 4 categories. So overall, this gated knowledge BERT framework, it combines our DAO with advanced NLP techniques to extract relationships between cannabis and depression. So these are the results. So these are the classes we have, and these are the examples of tweets on which we are able to identify the relationship in each input. Okay. So this is another use case where we analyze social media trends in substance use disorders for opioid listings on crypto markets. So the crypto markets is like listings looks like your Amazon product pages, and several opioids are listed on those crypto markets. And we're able to identify all this information from the ontology, and we're able to compare different drugs in the terms of sentiment and emotion and all. And these are the subreddits that we collected the data from. So over 70,000 opioid related listings were collected using a dedicated crawlers from this dark web crypto markets. And those files are then parsed and further proceeded to get all these substance names and product weight, price of the product, shipment information and all. And then what we did is we collected, so for all the drugs we identified on the crypto markets, we collected the related social media data from these subreddit groups. So that is how we got the trends from. So basically we are trying to see the reflection of dark web crypto markets on social media data. And we also moved one step forward and tried to detect addiction on social media. So for this, we use both social media data and dark web data. And so this is where we start at product listings. And then we have web crawlers and XPath processing, and we use drug abuse ontology to get the entities of interest. I mean, our drug names, substance names, obviously. And then after drug identification is done, we look for its reflection on social media, where we get data from Twitter and Reddit. And then we have bird-based models here that are used to generate sentiment and emotion. So what we have done here is we used a historic sentiment and emotion, like a temporal aspect associated with each data. And then we try to integrate that in our model and predict if that post is associated with substance use disorder or not. So this end-to-end system enables us to detect SUD, I mean substance use disorder trends, and we are able to make a public health intervention by analyzing reflection of dark web on social media. So this is the pipeline just for this block, knowledge-aware time series analysis. So this is the pipeline. So this is a knowledge-aware bird-based model which performs sentiment and emotion analysis on social media data. And we have set of historical posts. And this is the drug post to be assessed. And these are the historical posts. And we built this model. And each post here is associated with drug, a name, and a historical post related to that drug, and temporal aspect, which is time at which they are posted, and emotion and sentiment of the drug, we are able to identify in the data set. So those are the features for the drug to be assessed, if it is falls under SUD category or not. Basically, we are trying if that person is addicted or not. So substance use disorder means if there is a mention of substance abuse in the post or not. So we have encoding representing the sentiment and emotion spectrum, and we have sequential models such as RNN and LSTM models, which are great ways to encode representation that learn from a sequence where we have temporal aspect especially. And then we pass the historical post through this bidirectional LSTM and attention layer concatenated with the post to be assessed. And finally, we use softmax function to get detect or output the probability of SUD in that post. Okay, so this is error analysis we have done. We analyze the source of errors and discuss the predictions made by our model. So the error type here is a polydrug use. That means mention of multiple drugs in single post. And this post, there is a post level ambiguity here. And we have found sarcasm in this post. So it is very difficult in that case to make the prediction. So this is the error analysis of the model. So SUDP here is present and A is absent. Okay, so these are the key takeaways from this work. So we have seen how does knowledge help in the epidemiology domain and the knowledge sources that we used and the data sources from where we got our data. And these are the findings. So we are able to find novel drugs on dark web, and we're able to find association of mental health disorder with cannabis, and we're able to differentiate mental health symptoms along with gender and disease. And we also saw the reflection of dark web on social media using external knowledge. And this is a real impact we're able to make out of this study. Okay, so these are the publications. Sorry, this is not working. Okay, so I have so those works are published in journals and journals like JMAR and Plus One and BMC, and some of the works are presented at ICWSM, which is a social media related conference. Okay, I would like to acknowledge all my collaborators here, starting with Dr. Amish Sheth, and Dr. Valerie Shalin and Dr. Raminta and Dr. Amitava Das and Dr. Vignesh Narayanan as my dissertation committee today. And I also got an opportunity to work with several other collaborators who inspired me a lot, and I learned a lot from them when I'm working with them on grant projects and proposals. And also, especially the interdisciplinary experts here, like the CVD idea of gender, studying gender related mental health symptoms is from Dr. Mary Mariam Panahizar from UCSF. And all the cannabis and dark web related studies are from Dr. Raminta and Dr. Francois Lamy and Dr. Robert Carlson. Yeah. And DAO, you're perfect. Oh, ontology and evaluating the drug abuse ontology. That is a collaboration with Dr. Emily, who is expert in designing and ontologies and evaluation process. And yeah, and Dr. Manas Gaur and Kaushik Roy and Shweta Yadav and Utkarshni, they are my colleagues at Artificial Intelligence Institute here, and they inspired me to work with several knowledge-based approaches, causal-based approaches, and those formed a foundation for my work today. And yeah. Okay, so these are my mentees who are now researchers at eBay Seattle. Dr. Emmanuel Alambo and Orchid is at a PhD student now at IIIT Delhi. So we worked more closely and we are able to publish all this work in conferences. So it's a great opportunity to mentor them, and I understood what it takes to mentor them and the challenges we faced along the way. And it's a great learning experience for me and also for the mentees. And yeah. So this is the overview of my research vision and the methods I used and the application areas. And these are the collaborations and research grant funding. Those are the agencies and the grant numbers that funded. And the collaborators came from Sitar, Wright State University, Arnold School of Public Health, where the process knowledge guided models and the mild cognitive impairment detection work came from this group, and which is ABC at Arnold School of Public Health. And yeah. And we're able to disseminate research in several conferences through media articles, invited talks, and tutorials. Okay. So this talks about the several tutorials and invited talks we made as a contribution to the research community. Okay. And these are the resources where we published our drug abuse ontology, and the lexicon and drug use and depression lexicon is in here. And these are the grant proposals that are comes from different domains: mental health, drug use, and we have NSF and NIH grants. And these are the project titles that I work with. So these are the wiki pages where you can find more information on the work done, work demo today. And these are the references. And I would like to thank you everyone for listening to this elaborated presentation, for being so patient with me. Thank you.
Okay, thanks. Any questions? I'm signing out, sorry. It's okay if you don't have questions. Thank you, Usha.
Thank you.